Welcome to Orbit into Sleep. I'm so glad you found your way here tonight. Get yourself comfortable. Pull your blanket up a little. Let your shoulders drop. You've made it to the end of your day, and this moment right now, this is yours. Tonight, we are drifting out into the universe together. Far, far out into deep space, where some of the most ancient and beautiful stars in existence are slowly, quietly glowing. We're talking about red giants, these enormous, extraordinary stars that burn with a soft amber light. Stars so large, so old, so full of secrets, that just thinking about them has a way of making your own worries feel very, very small. The title of tonight's video is Relaxing Space Red Giants Facts to Fall Asleep To. And before we begin our journey, I just want to gently mention, if you're enjoying what we do here at Orbit into Sleep, it means the absolute world to us if you could take a moment to like this video and subscribe to the channel. It really does help other people who are lying awake tonight, just like you, find their way here too. We'd love for them to find a little peace, the same way you have. And if you feel like it, we'd love to know in the comments, roughly how many hours of sleep do you normally get per night? There are no wrong answers, whether it's 4 hours or 9. We're just curious about you. Now then, lights are low, your body is still. Let's begin. Tonight, we begin at the very beginning with the birth of something ancient. Imagine a star, not unlike our own sun, sitting quietly in space, going about its business for billions of years, burning hydrogen in its core, steady and faithful, held together by a perfect balance between the enormous weight of gravity pulling inward and the energy of nuclear fusion pushing outward. For billions of years, this balance holds. The star is stable, peaceful in a way. But stars are not permanent, and slowly, inevitably, the hydrogen begins to run out. When the fuel at the center of a star is finally exhausted, something remarkable happens. The core, no longer supported by the heat of fusion, begins to contract. Gravity, which had always been waiting patiently, begins to win. The core squeezes inward, growing denser and hotter, and all of that heat radiates outward into the layers of hydrogen that surround it. Those outer layers warm up, and then they ignite. Hydrogen fusion begins again, but this time not in the core, in a shell around it. And that shell burns so powerfully, so intensely, that it sends a wave of energy outward through the entire star. The outer layers, the great envelope of gas that makes up most of the star's body, begins to expand. Slowly, over millions of years, the star swells. It grows. It becomes something new. It becomes a red giant. Now, here is something quite beautiful to think about as you settle in. This expansion, this transformation, can increase a star's radius by a factor of 10, 50, sometimes 200 times its original size. Our own sun, one day, will swell so large that it reaches roughly where the Earth currently orbits. The same quiet star that warms our faces on a summer afternoon will one day become something vast and luminous and amber-colored, filling a great portion of the inner solar system. But that is 5 billion years from now, so perhaps don't worry about it tonight. As the star expands, something else happens too. The surface temperature drops. The star is spreading its energy across a much, much larger area. And so the outer layers cool from the brilliant white-blue of a young star to a deep, warm, reddish-orange glow. Between about 3,000 and 5,000 Kelvin, the star's light shifts toward the red end of the spectrum, and that, simply and beautifully, is why we call them red giants. Astronomers actually have a lovely way of describing this process. They call it the mirror principle. As the inner layers of the star, specifically the hydrogen-burning shell at its heart, contract inward, the outer envelope responds by doing the opposite. It expands outward. The two halves of the star mirror each other. One compresses, one blooms. It is a kind of cosmic breathing, a slow and ancient exhale that the star has been building toward for its entire life. For stars between about half the mass of our Sun and roughly 8 solar masses, this red giant phase is essentially inevitable. It is written into the physics of stars from the moment they are born. Every star in that range, and that includes the vast majority of stars we can observe, will one day expand, cool, and glow with that deep, warm light. The stars most people are familiar with in our night sky, the bright, steady, amber-colored points of light, many of those are already red giants. They have already passed through their hydrogen-burning youth and entered this slower, more expansive chapter of their lives. They are old stars, and there is something deeply calming about that when you think about it. Older, larger, softer in color. As you lie there, let your breathing slow a little. Let your chest rise and fall at whatever pace feels easy. You don't need to do anything right now. The stars certainly aren't rushing. Now, as a red giant climbs toward the peak of this phase, something wonderful happens deep inside it. The convective envelope, the churning outer layers of the star that are constantly mixing and moving like a vast, slow ocean, begins to reach down deeper into the star. It dips into the layers where nuclear reactions have already taken place, and it brings some of what it finds there up to the surface. This is called the first dredge up, and it is one of the more poetic moments in a star's life. Elements forged in the nuclear reactions of the star's earlier life, helium, nitrogen, the products of the CNO cycle, are carried upward by this great convective motion and mixed into the outer layers. If you were somehow able to take a spectrum of a red giant's surface, you would see the chemical fingerprints of its deep interior written into its light. The star, in a sense, is bringing its inner life to the surface. There is something rather tender about that. Now, the phase we've been describing, where the star is ascending this great arc of expansion, becoming more and more luminous and larger, astronomers call this the red giant branch. The star is quite literally climbing a path on the diagram that maps stellar temperature against luminosity, a diagram called the Hertzsprung-Russell diagram, or the HR diagram. As a star ascends the red giant branch, its luminosity increases, sometimes reaching 3,000 times the brightness of our Sun, while its surface temperature remains relatively cool. The star is becoming genuinely enormous, and as it grows, the helium core at its center is growing too. contracting, compressing, becoming ever denser, waiting. Because the next chapter, the chapter that ends the red giant branch, involves one of the most dramatic events in all of stellar physics. But we'll come to that gently. For now, just let yourself rest with this image. A vast amber star glowing warmly in the dark of space, its outer layers moving in great slow currents like clouds seen from very far away. Its surface cool enough by stellar standards to begin forming tiny mineral grains in its outer atmosphere. The first whisper of dust. These are the oldest, most evolved members of the stellar community. They have been shining since long before our planet existed, and they will continue their quiet, luminous work long after tonight's worries have dissolved into sleep. Let your eyes feel heavy. Let the weight of your body sink into wherever you're resting. The universe is very large and very old and very quiet, and tonight you are a small and peaceful part of it. We left our red giant climbing, growing larger, more luminous, its helium core quietly contracting beneath all those vast outer layers, becoming denser, hotter, waiting for a moment that has been building for billions of years. For stars like our sun, stars below roughly 2¼ solar masses, something extraordinary happens to that core as it contracts. The density becomes so extreme, millions of grams per cubic centimeter, that the electrons inside it are squeezed into a very unusual state, a state governed not by heat or pressure in the ordinary sense, but by one of the fundamental rules of quantum mechanics, the Pauli exclusion principle. This principle, named after the Austrian physicist Wolfgang Pauli, states that no two electrons can occupy exactly the same quantum state at the same time. When matter becomes dense enough, the electrons run out of room. They are packed so tightly that they resist further compression simply because the laws of physics will not allow them to be squeezed any closer together. This resistance is called electron degeneracy pressure, and it is entirely independent of temperature. The core can get hotter and hotter, but the pressure holding it up doesn't change. There is no safety valve, no way for the core to expand gently in response to rising heat. This sets the stage for something quite spectacular. As the helium core continues to contract and heat up inside our red giant, it eventually reaches a temperature of around 100 million Kelvin, 100 million. And at that temperature, helium fusion ignites. In a normal, non-degenerate core, this would be a smooth and self-regulating process. The core would heat up, expand slightly, cool down a little, and the fusion reaction would settle into a steady rhythm. But in a degenerate core, that self-regulation doesn't exist. The heat from fusion cannot cause the core to expand, so the temperature rises. And as the temperature rises, the fusion rate increases, which releases more heat, which raises the temperature further, which increases the fusion rate again. A runaway reaction, unstoppable and extraordinarily fast. This event is called the helium flash. Now, here is the part that I find almost impossibly wonderful. At the peak of the helium flash, which lasts only a matter of minutes, the energy being released in the core of the star can rival the luminosity of an entire galaxy, 100 billion stars worth of energy pouring out of a volume smaller than the Earth in just a few minutes. And yet, you would never know it was happening if you were watching from outside, because almost none of that energy reaches the surface. Every last bit of it is absorbed by the process of lifting the degeneracy. All of that enormous flood of energy goes into expanding and cooling the core, converting it from that strange compressed quantum state back into ordinary hot gas. The core blooms outward. The hydrogen-burning shell above it, suddenly deprived of the intense pressure from below, cools and dims, and the star, rather than brightening dramatically, actually contracts and becomes less luminous for a time. The most powerful event in the star's life passes in near total silence, hidden deep inside, invisible from the outside, a secret kept in the heart of the star. After the helium flash, the red giant settles into a calmer phase. The core, now a normal gas again, begins fusing helium steadily into carbon and oxygen through what is called the triple alpha process. The star contracts to a smaller, hotter, more stable configuration. Astronomers call this the horizontal branch, and for about 100 million years, the star simply burns, quietly, steadily, content in its way. The triple alpha process itself is worth dwelling on for a moment. It is, in a very real sense, the reason you exist. To fuse helium into carbon, a star must perform a rather delicate trick. Two helium nuclei fuse together to create beryllium-8. But beryllium-8 is extraordinarily unstable. It survives for only about 100 quadrillionth of a second before falling apart again. In ordinary circumstances, this would be the end of the story. No carbon would ever form. But inside the dense, hot core of a red giant, the density is so high that before that beryllium-8 can decay, a third helium nucleus collides with it, and the result is carbon-12, stable, lasting, beautiful carbon-12. Carbon, the foundation of organic chemistry, the backbone of every protein, every cell, every living thing on Earth. All of it forged in moments like this, in the hearts of ancient red giants, billions of years before our solar system existed. You are, in the most literal sense, made of star stuff, and the stars that made you were red giants. Gently now, let that settle. Let your body feel heavy and warm. Let your thoughts move slowly, like those great convective currents in the outer layers of a star, not rushing anywhere, just turning, softly and slowly in the dark. The horizontal branch phase, where our star now sits burning helium in its core, lasts around 100 million years. That is an almost incomprehensible stretch of time. 100 million years ago on Earth, dinosaurs were still walking the planet, and yet for a star, this is just one quiet chapter, one steady, unhurried period of burning before the next transformation begins. For more massive red giants, those above roughly 2.5 solar masses, the helium flash never happens at all. Their cores never become degenerate. When helium ignites in those stars, it does so smoothly and gently, without drama, without the hidden explosion, without the secret kept in the heart. They simply begin fusing helium and carry on. There is something rather lovely about that contrast. The smaller stars, the ones more like our sun, carry their most dramatic moment entirely within themselves, invisible to the universe, while the more massive stars transition quietly, unremarkably, into their next phase. Both paths lead eventually to the same place. When the helium in the core is finally exhausted, the cycle begins again. The carbon-oxygen core contracts. A helium-burning shell ignites around it, and above that, a hydrogen-burning shell continues its work. Two shells now, nested inside each other, each burning at their own pace, driving a new and even more dramatic expansion. This is the asymptotic giant branch, the AGB, and it is where red giants become truly, breathtakingly enormous. AGB stars can reach luminosities of 10,000 times the Sun. Their radii can stretch to 200 solar radii or more. They are among the largest and most luminous cool stars in the entire universe, and they are restless. Their interiors are punctuated by brief, explosive events called thermal pulses, where the helium shell periodically ignites in a burst of energy every 10,000 to 100,000 years or so, stirring the star's interior and driving great waves of material toward the surface. It is during these thermal pulses that something extraordinary happens to the star's chemistry. The third dredge-up, a deep mixing event triggered by the pulse, can carry carbon all the way to the surface. If enough carbon accumulates, the star crosses a threshold where carbon becomes more abundant than oxygen in the outer layers. The star becomes a carbon star. Its spectrum changes, its dust changes, it begins shedding carbon-rich grains into the surrounding space. These grains, scattered by stellar winds across the interstellar medium, will one day become the raw material for new stars, new planets, perhaps somewhere, new life. The AGB phase is the star's great final act of generosity. Everything it has built, everything it has forged in millions of years of nuclear burning, it now begins to give away. And all of this, every step of it, from the first quiet expansion of the subgiant phase, through the helium flash, the horizontal branch, and now the vast, restless luminosity of the AGB, all of it was set in motion by the simple exhaustion of hydrogen in the core. One fuel runs out, and the star reinvents itself again and again, more beautifully each time. Let your breathing be slow and easy. The night is quiet. The stars outside, if you could see them right now, are doing exactly what they have always done, burning, evolving, slowly and patiently working their way through their long, luminous lives. You don't need to go anywhere. You don't need to do anything. Just rest here. here in the dark while the universe carries on around you, vast and ancient and entirely unconcerned with the time. There are stars in the night sky that you can see with your naked eye on a clear night that are already red giants, already in that great expanded phase we have been talking about. And some of them have names that humans have been using for thousands of years. Let's visit a few of them tonight, quietly, like passing by lit windows on a slow evening walk. The first is Arcturus. Arcturus is the brightest star in the northern constellation of Boötes, and on a clear night in spring or summer, it is one of the most prominent stars in the entire sky. It has a warm, distinctly amber color that sets it apart from the cooler blue-white stars nearby. And that color is not coincidental. Arcturus is a red giant, a classic example of a star on the red giant branch, glowing at a surface temperature of around 4,200 Kelvin. What makes Arcturus particularly interesting is how unremarkable it is in terms of mass. It is only very slightly more massive than our own Sun, around 1.08 solar masses. And yet it has expanded to 25 times the Sun's radius. 25 times. If you placed Arcturus where our Sun currently sits, it would be an enormous amber sphere filling the inner solar system with warm light. And it is only 36 light years away. In cosmic terms, that is practically next door, close enough that astronomers can measure its properties with exceptional precision. Arcturus also has a piece of human history woven into it, which I find rather lovely. In 1718, the English astronomer Edmund Halley, the same Halley of the famous comet, was comparing his star observations with ancient Greek star catalogs, and he noticed something puzzling. Arcturus was not where it was supposed to be. It had moved, not by much, but measurably, clearly, verifiably moved relative to where the ancient Greeks had recorded it. This was genuinely shocking at the time. Stars were supposed to be fixed. The background of the sky, permanent and unchanging. But Arcturus had drifted, and this observation helped establish something we now take completely for granted: that stars are moving through space, that the sky is not a fixed backdrop, but a slowly shifting collection of objects, each on its own journey through the galaxy. Arcturus, this quiet amber light that people had been navigating by and telling stories about for millennia, turned out to be a traveler. Not far away in the sky, if you know where to look, is another famous red giant, Aldebaran, the eye of the bull in the constellation of Taurus, a deep orange-red star that marks the angry gaze of the celestial bull and has done so in human mythology for thousands of years across many different cultures. Aldebaran is a little more evolved than Arcturus, a little further along its journey. Its radius is 44 times that of the Sun, and it shines with about 400 times the Sun's luminosity. It sits about 65 light years away, and its surface glows at a slightly cooler temperature, around 3,900 Kelvin, giving it that distinctly reddish tint. What I find particularly touching about Aldebaran is that it has a planetary companion. a Jupiter-like planet orbiting this ancient swollen star at a comfortable distance. A planet circling a red giant. A world that has watched its own star transform, that has experienced the gradual warming and brightening as the star expanded, and yet somehow persists, somehow remains. It reminds us that planets do not necessarily disappear when their stars age, that the story of a planetary system does not end when the main sequence does. Things change, certainly, dramatically, but they continue. Let your mind rest on that for a moment. Continuity, things carrying on, persisting through transformation. Now, if Arcturus and Aldebaran are the familiar faces of the red giant world, then Mira is something altogether more theatrical. Mira. The name comes from the Latin for wonderful, and it was named that in 1596 by the Dutch astronomer David Fabricius, who watched it appear in the sky, brighten over several months to become one of the most prominent stars visible, and then fade away entirely, vanishing below the threshold of naked eye visibility. He thought he had witnessed a new star appearing and then dying. He had no framework to understand what he was actually seeing. What he had found was a pulsating, variable star, the prototype of an entire class of stars that now bears its name, Mira variables. Mira is an AGB star in that final great expansive phase we discussed, and it pulses. Over a period of roughly 332 days, it brightens and dims in a slow, rhythmic cycle, driven by the expansion and contraction of its outer layers. At its brightest, Mira can be clearly visible to the naked eye. At its dimmest, you would need a telescope to find it at all. The same star, breathing in and out over the course of a year. But Mira has something else entirely, something that was only discovered in 2007 when NASA's Galaxy Evolution Explorer satellite captured an ultraviolet image that stunned astronomers. Mira has a tail, a 13 light-year-long tail of shed gas and dust streaming behind it as it moves through the interstellar medium at about 130 kilometers per second. 13 light-years. For reference, the nearest star to our own sun is about 4 light-years away. Mira's tail is more than 3 times that length, trailing behind it like the wake of a boat or the tail of a comet, but on a scale that staggers the imagination. That tail represents about 30,000 years of Mira's mass loss history, 30,000 years of stellar wind frozen in space, marking every place the star has been. A record written in gas and dust stretched across the galaxy. Mira is also in a binary system. It has a companion, a white dwarf, that it slowly orbits. Material shed by Mira occasionally streams onto this companion, which can cause periodic brightenings and outbursts. A red giant and the remnant of another red giant orbiting each other in the dark, each a different stage of the same long journey. And then there is Gacrux, Gamma Crucis, the top star of the Southern Cross, that iconic constellation of the Southern Hemisphere sky that has guided sailors and travelers for centuries. Gacrux is the nearest M-type giant to Earth, only 88 light years away. What makes Arcturus particularly interesting is its extreme ratio of expansion relative to its original mass. It is only about 30% the mass of our Sun, a rather small star by any measure, and yet it has expanded to 120 times the solar radius. An extraordinarily large, cool, slow-burning giant from a star that started out quite modest. Arcturus' surface temperature is around 3,400 Kelvin, making it one of the cooler red giants we can observe nearby. At that temperature, its light is deeply red, the color of a fading ember. These stars, Arcturus, Aldebaran, Mira, Arcturus, they are not abstract objects in a textbook. They are real physical places. Enormous spheres of luminous gas, each with their own history, their own chemistry, their own pace of evolution, each one burning through its final chapters at its own unhurried rate, and each one in the fullness of time will come to the same ending. As the AGB phase draws to a close, the thermal pulses become more frequent, the mass loss more intense. The stellar wind strengthens until it is carrying away the star's outer layers in great, slow streams. Over tens of thousands of years, the envelope is shed entirely. What remains behind is the hot, dense carbon-oxygen core, glowing fiercely as it is exposed to space. For a brief period, perhaps 10,000 years or so, the ultraviolet radiation from this hot core ionizes the expanding shell of ejected gas, causing it to glow in beautiful, intricate patterns. We call these objects planetary nebulae, not because they have anything to do with planets, but because early astronomers looking through small telescopes thought the round, glowing shapes resembled the disk of a planet. They are among the most beautiful objects in the observable universe, rings and bubbles and hourglasses of glowing gas lit from within by the dying star at their center, the ring nebula, the cat's eye, the helix, sometimes called the Eye of God, each one a red giant's final exhale, its last great creative act before the core cools and dims into a white dwarf roughly the size of the Earth, but carrying the mass of the Sun. Dense and quiet and slowly cooling over billions of years into the dark, it is a gentle ending for a long and generous life. Let that image sit with you for a moment. A glowing ring of color in the deep black of space. The final gift of an ancient star lighting up the neighborhood it has spent its whole life in, one last time before going quietly to rest. Your breathing is slow, your body is still. The night outside is full of light you cannot see, ancient light, traveling toward you across unimaginable distances, from stars in every stage of their long lives. Some of them are just beginning. Some of them, like Mira, are breathing their last great breaths. And somewhere out there, right now, a red giant is quietly, invisibly undergoing its helium flash. The most powerful event of its life, hidden completely, a secret kept entirely within itself. Rest now, let the images drift. There is no hurry anywhere in the universe tonight. Before we drift into our next chapter, I just wanted to mention something gently and briefly. If sleep is something you struggle with regularly, I've put together a few things in the description below that you might find helpful. Just some resources and ideas that I've come across. No pressure at all, and certainly no rush tonight, but if you're curious, it's there whenever you'd like it. Right, back to the stars. We have talked about how red giants are born, how they burn, how they pulse and swell, and eventually breathe their outer layers gently into space. But there is another layer to the story of these stars that is perhaps the most remarkable of all. Red giants are not just dying stars, they are factories, the most productive chemical factories in the entire galaxy. And the elements they forge and scatter into space are the very ingredients from which everything else, planets, oceans, atmospheres, and living things, is eventually assembled. Let us spend some time in that factory tonight. You will remember that the triple alpha process, that delicate three-step collision happening in the core of a red giant, produces carbon, and carbon is where the story of chemistry truly begins. Before red giants existed, the universe was almost entirely hydrogen and helium. Everything heavier, every element that makes complex chemistry possible had to be built. And the red giant phase, particularly the AGB phase, is where much of that building happens. But carbon is only the beginning. Inside an AGB star, during those periodic thermal pulses we mentioned, something else is happening alongside the helium burning. Neutrons are being released, not in enormous quantities, but in a slow, steady trickle. And these free neutrons drift through the stellar interior, encountering the nuclei of whatever elements are already present. Iron, mostly, iron that was there when the star was born, inherited from the gas cloud it formed from. And when a neutron is captured by an iron nucleus, the nucleus becomes heavier. Its atomic number stays the same, but its mass number increases. If the result is unstable, it undergoes beta decay, converting a neutron into a proton and releasing an electron. And suddenly the nucleus has one more proton than it had before. It has become a different element. This process, slow neutron capture, is called the S process, and it is responsible for roughly half of all the elements heavier than iron in the universe. Take a moment to sit with that. Half of everything heavier than iron. Strontium, yttrium, zirconium, barium, lanthanum, cerium, all the way up to lead and bismuth. All of it built, one neutron at a time, inside the hearts of AGB stars, inside red giants. The elements are then carried to the stellar surface by those great dredge-up events we mentioned, mixed into the outer layers, and eventually expelled into space by the stellar wind, where they drift through the interstellar medium for millions of years until a new gas cloud collapses, a new star forms, and the cycle begins again. The sun and the solar system and the earth and you are all made partly of material that passed through the interior of a red giant. The iron in your blood was made in a supernova, but the barium in your body, the strontium in your bones, the lead in old paint, the zirconium in certain ceramics, all of that was built slowly and patiently in the interior of an AGB star billions of years ago by a process that takes one careful neutron capture at a time. There is something extraordinarily patient about the S process. It is not explosive or violent, like the rapid neutron capture that happens in supernovae. It is slow, methodical, one step at a time, building heavier and heavier nuclei over thousands of years inside the warm interior of an ancient star. There is a wonderful moment in the history of astronomy that proved this was really happening. Not as a theory, not as a model, but as an observed, real-time fact. In 1952, the American astronomer Paul Merrill was studying the spectrum of a class of stars called S-type giants, and he found something that should not have been there. An absorption line corresponding to the element technetium. Technetium, element 43 on the periodic table, the lightest element with no stable isotopes whatsoever. Every form of technetium is radioactive. The longest-lived isotope, technetium-99, has a half-life of only about 210,000 years. In cosmic terms, that is nothing. The universe is 13.8 billion years old. Any technetium that existed when the solar system formed 4.5 billion years ago would have decayed into nothingness long, long ago. There should be no technetium in any star. And yet there it was, in the spectrum of a red giant, unmistakably present. The only possible explanation was that the technetium had been made recently, inside the star itself, by nucleosynthesis happening right now, and then dredged up to the surface. Merrill had found the smoking gun, direct observational proof that nuclear reactions were occurring inside living stars and that their products were being mixed to the surface in real time. It was one of the most elegant confirmations in the history of astrophysics. A single spectral line, a tiny dip in a graph of starlight, that proved that the elements are being built inside stars as we watch. Let that thought gently unfurl as you breathe. The light from a distant red giant passing through a spectrograph, revealing the signature of a freshly made element. A window into the nuclear heart of a star, opened by a single line in a spectrum. Now, alongside the S process, red giants are also involved in one of the longer-standing puzzles in stellar astrophysics, something called the lithium problem. Standard models of stellar evolution predict that when a star ascends the red giant branch and undergoes the first dredge-up, the deep mixing of its outer layers should destroy any lithium present near the surface. Lithium is a fragile element. It burns at relatively low temperatures, around 3 million Kelvin. Once the convective envelope reaches deep enough to expose material to those temperatures, the lithium should be gone. And in most red giants, it is. Surface lithium abundances are low, just as the models predict. But in about 1% of red giants, the lithium is not gone. It is abundant, extraordinarily abundant. Some of these stars, called superlithium-rich giants, have surface lithium levels that actually exceed the primordial abundance from the Big Bang itself. They have more lithium on their surfaces than the universe started with. How is that possible? The answer lies in a mechanism called the Cameron-Fowler process. Deep in the hydrogen-burning shell, a series of reactions can produce beryllium-7. If this beryllium-7 is rapidly carried by mixing currents to cooler regions of the star before it can react further, it decays into lithium-7 via electron capture. Lithium, freshly made, deposited in the cooler outer layers of the star. For this to work, the mixing has to be fast. Faster than standard convection models predict. Something extra is needed, and astronomers are still working out exactly what that something is. Candidates include a process called thermohaline mixing, driven by slight differences in chemical composition, creating instabilities in the stellar interior, internal gravity waves rippling through the star from the turbulent boundary of the convective zone, and in some cases, the engulfment of a planet. Yes, a planet. There is evidence that some lithium-rich giants became that way by swallowing a companion planet. As the star expands on the red giant branch, the orbits of nearby planets decay. Tidal forces draw them inward, and eventually, the planet spirals into the star's envelope and is absorbed. The disruption this causes can trigger extra mixing, and the material of the planet itself, rich in lithium relative to the stellar surface, contributes to the enrichment. One striking example is a star called BD plus 48740. It has unusually high lithium and also hosts a companion planet in a highly eccentric orbit. The eccentricity suggests that another planet, once orbiting closer in, was recently disrupted and consumed. The star may have eaten its inner planet, and the evidence is written in its chemistry. There is something almost melancholy about that. A star, in its old age, drawing its children back into itself. As you let your thoughts drift, consider this. Every element you can think of has a story, a journey. It was made somewhere by some specific process in some specific environment. It was scattered. It drifted. It was gathered again. It became part of something new. And whatever that new thing was, it too eventually transformed. The calcium in your teeth was forged in a dying massive star. The oxygen in your lungs was made partly in red giants. The carbon that forms the chains of your DNA was built in a triple alpha reaction in a stellar core billions of years before the Earth existed. You are the end product of billions of years of stellar chemistry, patient, cumulative, extraordinary. And right now, that extraordinary thing is lying in the dark, breathing slowly, drifting toward sleep. That seems just about right. Let the facts settle gently into the background, like sediment drifting to the floor of a still, deep lake. You don't need to hold on to any of it. Just let it be there, softly, as your mind begins to go quiet. The universe is still making elements tonight. In red giants thousands of light years away, neutrons are being captured. Nuclei are growing heavier. New atoms are being built for the first time. It has been happening for billions of years. It will happen for billions more. And through all of it, the stars just quietly burn. We have traveled quite far tonight, from the birth of a red giant through its helium flash, its long, slow burning, its chemical generosity. We have visited famous stars by name, and we have watched them shed their outer layers in glowing rings of color. We have followed atoms from stellar cores to living cells. Now let us go a little deeper into some of the stranger, more surprising things that astronomers have discovered about red giants in recent years. Things that challenge what we thought we knew. Things that are still being worked out even now in observatories and on computer screens and in the pages of journals that were published just last year. Because science, like the stars themselves, is never quite finished. Let us begin with something that sounds almost contradictory: the way we study the insides of stars by listening to them. Stars make sound, not sound that travels through space, because space carries no sound, but pressure waves that travel through the interior of the star itself, making the whole surface oscillate, expand, and contract in patterns that repeat over hours or days. These oscillations are extraordinarily small. The surface of the sun moves by only a few meters per second during a typical oscillation, but they are detectable from space by satellites sensitive enough to measure the tiny changes in brightness that accompany each pulse. This field is called asteroseismology, the seismology of stars. Just as geologists can map the interior of the Earth by studying how earthquake waves travel through it, astronomers can map the interior of a star by studying how these oscillations behave. And red giants are particularly rich subjects for this kind of study because they exhibit something called mixed modes. In a red giant, some oscillations behave like pressure waves, bouncing around in the outer convective envelope. Others behave like gravity waves, sloshing back and forth in the deep radiative core. And in a red giant, these two types of wave can couple together, creating hybrid oscillations that carry information from both the surface layers and the deep interior simultaneously. This is extraordinary. It means that by carefully analyzing the pattern of oscillations on the surface of a red giant, astronomers can learn about conditions deep inside the star. The rotation rate of the core, the strength of magnetic fields buried far below the surface, the boundary between the convective envelope and the radiative interior. All of this encoded in the flickering brightness of a distant star. The Kepler Space Telescope, which operated from 2009 to 2018, observed hundreds of thousands of stars continuously for years, measuring their brightness with extraordinary precision. And the data it gathered on red giants has transformed our understanding of stellar interiors. One of the most puzzling things that Kepler revealed was about rotation. When a star evolves off the main sequence and its core contracts, the laws of physics suggest that the core should spin faster. Conservation of angular momentum, the same principle that makes a spinning ice skater speed up when they pull their arms in. As the core shrinks, it should spin up. Models predicted that red giant cores should be rotating extremely rapidly, hundreds of times faster than the surface. But when astronomers used asteroseismology to actually measure the core rotation rates of red giants, they found something completely different. The cores were rotating slowly, nearly 2 orders of magnitude slower than the models predicted. Something was breaking the core, transferring angular momentum from the fast-spinning core to the slower outer envelope, keeping them more or less coupled. But what? The leading candidate is magnetic fields. Specifically, magnetic fields generated deep inside the star by a process called the Taylor-Spruitt dynamo, where differential rotation between layers of different density creates and sustains a magnetic field that acts like a coupling mechanism, transferring spin from the core outward. Like a magnetic clutch, quietly and continuously equalizing the rotation rate between the deep interior and the outer layers. There is something beautiful about that image. A magnetic field, invisible and intangible, threading through the interior of a star, gently, persistently, keeping the whole thing turning together. And yet even this explanation has complications, because when astronomers surveyed a large sample of red giants, they found that the core rotation rates did not fall on a smooth continuum. They clustered into 2 distinct groups, 2 peaks, stars where the core rotates with a period of around 18 days, and stars where it rotates with a period of around 12 days. A bimodality, a split. Why 2 groups? What determines which group a star falls into? Is it something about the star's history on the main sequence, the efficiency of its internal magnetic dynamo, the presence or absence of a companion star? These questions do not yet have definitive answers, and that, honestly, is one of the things I find most wonderful about modern astronomy. We have instruments sensitive enough to measure the rotation rate of the core of a star thousands of light years away. And what those instruments tell us is that there is still so much we do not understand. The universe keeps its secrets well. Let your thoughts drift gently here into the idea of a star with a secret interior, a slowly rotating core coupled to its envelope by invisible magnetic fields, oscillating in patterns that carry information about its deepest layers up to the surface, where we can read it if we are patient and careful and have the right instruments. There is another remarkable discovery that came out of studying red giants in binary systems. Systems where a red giant orbits alongside another object. And in some extraordinary recent cases, that other object is a black hole. In 2023 and 2024, astronomers using data from the Gaia satellite announced the discovery of 2 systems called Gaia BH2 and Gaia BH3, in which a red giant is orbiting a dormant stellar mass black hole. Not an active black hole, not one that is currently consuming material and blazing with X-rays. A quiet one, simply sitting there, invisible, detectable only through the gravitational influence it exerts on its companion. Gaia BH2 is particularly interesting from an asteroseismic perspective. The red giant in that system has been studied in detail, and its oscillations reveal a star that is rotating faster than it should be for its age. Its rotation has been sped up, or at least maintained at a higher rate than expected, by tidal forcing from the black hole's gravity. The black hole is not consuming the star. It is not even close enough to distort it visibly. But its gravitational presence is subtly influencing the star's rotation, leaving a fingerprint in the astroseismic data. A black hole, making itself known through the spin of a star. Gaia BH3, meanwhile, presented a different puzzle entirely. Based on the red giant's size, temperature, and luminosity, it should be oscillating with amplitudes large enough to detect easily with the TESS satellite. But when astronomers looked, there was nothing, no oscillations, or at least none that could be detected above the noise. Why would a red giant that should be oscillating simply not be? One possibility is that the magnetic field in BH3's companion is suppressing the oscillations. Magnetic fields can damp the oscillations of red giants, a phenomenon sometimes called the magnetic greenhouse effect, where the wave energy gets trapped and dissipated in the magnetized core rather than reaching the surface. In some red giants, this suppression affects only certain modes, creating what are called depressed dipole modes. But in BH3, if magnetic suppression is the explanation, it appears to be operating at an unusual scale. Another possibility still being investigated is that the tidal interaction with the black hole is disrupting the oscillation patterns in ways that our current models do not fully account for. The honest answer is that we don't entirely know yet, and BH3 sits in the literature as an open question. A red giant next to a black hole, quietly not oscillating, waiting for someone to figure out why. I find something deeply peaceful about open questions like that. They are not gaps or failures. They are invitations, places where the universe is still holding something back, waiting for the right question, the right instrument, the right moment of insight. Settle a little deeper now. Let your muscles soften. The questions can wait. They have been waiting for years in some cases, and they will still be there tomorrow. There is one more strange thing worth knowing about red giants tonight before we let the science fade into the background. Something discovered very recently in 2025 that turned a long-standing assumption on its head. For decades, the standard understanding was that red giants with higher metallicity, meaning stars that contain more heavy elements, more metals in the astronomer's sense of the word, should lose more mass as they evolve up the red giant branch. The reasoning was straightforward. More metals mean more opacity. More opacity means radiation pressure can more efficiently drive a stellar wind. More wind means more mass loss. It made perfect sense. It was in the textbooks, and it appears to be wrong. New measurements using a combination of astroseismic data and stellar population studies found that the total amount of mass lost by a red giant as it climbs the red giant branch actually decreases with increasing metallicity. Metal-rich stars, by this account, lose less mass, not more. The exact reason is still being worked out. It may relate to how surface gravity and temperature interact at different metallicities, or to the way the stellar wind couples to the underlying physics of the chromosphere. But whatever the cause, the implication is significant. Our models of how red giants contribute material to the galaxy, how they enrich the interstellar medium, how they affect the chemical evolution of stellar populations, all of those models were built on an assumption that now needs to be revisited. Science, doing what science does, quietly, persistently correcting itself. The red giant branch is not a settled story. It is an ongoing investigation conducted by thousands of astronomers around the world, with telescopes in space and on mountaintops and buried in archives of data still waiting to be fully analyzed. And in the meantime, the stars themselves are completely indifferent to our models. They simply do what physics requires them to do, at their own pace, in their own time, burning and pulsing and shedding and transforming, whether we understand them or not. There is something rather freeing about that. The universe does not require our understanding in order to function. It just carries on, enormous and ancient and quietly extraordinary, just as sleep does not require you to understand it. You do not need to know the neuroscience of slow-wave sleep, or the function of the glymphatic system, or the role of adenosine in building sleep pressure. You just need to let go, to stop holding on, to allow the thing that your body already knows how to do to simply happen. The stars are burning, the questions are being asked, the universe is carrying on, and you, right now, are exactly where you need to be. Let your thoughts soften at the edges. Let the images we have moved through tonight, amber stars, glowing rings, magnetic fields threading through stellar cores, the quiet drift of neutrons through ancient interiors, let them become softer now, less distinct, more like a feeling than a picture. You have learned a great deal tonight, and now you can let all of it rest. We are moving into the quieter hours now, the part of the night where the world outside has gone still and even your thoughts are beginning to lose their edges. This is a good place to be. Let us spend this last chapter in the most peaceful part of our journey, out at the very edges of what red giants become, in the dust and the light and the slow, generous ending of a stellar life. When an AGB star is in its final phase, shedding its outer layers through increasingly powerful stellar winds, something remarkable happens in the space immediately surrounding it. The gas streaming away from the star begins to cool, and as it cools, it condenses. Tiny solid grains begin to form. Mineral grains crystallizing out of cooling stellar gas, the way frost forms on a cold window on a winter morning. These grains are extraordinarily small, typically less than a micron across, smaller than the wavelength of visible light. And yet they are there, drifting outward through the expanding envelope of the dying star, growing slowly as more gas condenses onto their surfaces. The mineralogy of these grains depends on the chemistry of the star that made them. In oxygen-rich AGB stars, where oxygen is more abundant than carbon, the grains that form are silicates and oxides, minerals that are, in many cases, the same minerals found in the rocks of the Earth. In carbon-rich AGB stars, where the third dredge-up has tipped the balance in favor of carbon, the grains are different. Silicon carbide, graphite, carbon-rich compounds of extraordinary complexity. Some of these grains, the most durable ones, survive the entire journey through the interstellar medium intact. They are incorporated into new gas clouds, new planetary systems, new planets. They are found today, preserved inside primitive meteorites, ancient rocky bodies that have not been significantly altered since the early solar system. These grains are older than the sun, older than the Earth. They are, in the most literal sense, stardust. The physical remains of stars that lived and died before our solar system existed. When scientists analyze these pre-solar grains in the laboratory, they can read their chemistry like a fingerprint, identifying which type of star made them, what its isotopic composition was, how far along in its evolution it was when the grain condensed. Each tiny grain is a message from a dead star, preserved for billions of years, waiting to be read. There is something almost unbearably beautiful about that. A grain of dust, smaller than a bacterium, carrying within its crystal structure the story of a star that burned out before the sun was born. Let that image settle very gently, something so small carrying something so old. Now, in the infrared light of these dusty, stellar envelopes, astronomers have found some fascinating and still mysterious features. Specific wavelengths at which the dust glows particularly brightly, corresponding to the vibrational frequencies of particular mineral species. There is a feature at 13 micrometers in the mid-infrared that puzzled astronomers for decades. It appears in the spectra of oxygen-rich AGB stars, a distinct bump in the thermal emission of the dust shell, and identifying its carrier turned out to be surprisingly difficult. The current best candidates are corundum, which is the mineral form of aluminium oxide, and spinel, a magnesium aluminium oxide. Both are high-temperature condensates, minerals that form at temperatures above 1,000 Kelvin, very close to the star's surface. Corundum, incidentally, is the same mineral as ruby and sapphire. The colors differ because of trace impurities. Pure corundum is colorless, but in the right conditions, with a little chromium or iron in the crystal structure, you get gemstones of extraordinary beauty. And here it is, forming in the outflows of dying stars in tiny grains scattered across the galaxy. There is another feature, a broad bump at around 30 micrometers that is even more mysterious. It appears in the spectra of both oxygen-rich and carbon-rich AGB stars, and its carrier is still debated. The leading candidate is magnesium sulfide, but the identification is not definitive. Astronomers call it the 30 micrometer bump, and it sits in the literature as one of those comfortable open questions, acknowledged, studied, not yet fully resolved. The universe, as we have established, keeps its secrets well. As the dust shell expands and cools and the central star gradually exhausts its remaining fuel, the system enters its final transformation. The mass loss slows, the envelope thins, and the hot core of the star, which has been hidden beneath all those layers of gas and dust, begins to be exposed. This newly revealed core is extraordinarily hot, initially hundreds of thousands of Kelvin, and its ultraviolet radiation floods outward into the expanding shell of ejected material, ionizing it, causing it to fluoresce. The planetary nebula ignites. We mentioned these briefly earlier, but let us spend a little more time with them now because they deserve it. Planetary nebulae are among the most visually extraordinary objects in the observable universe. Each one is unique. The geometry of the ejected envelope, shaped by the star's rotation, by the presence of a companion, by magnetic fields and pulsations, and the complex fluid dynamics of stellar winds, create structures of astonishing variety and intricacy. Some are simple spherical shells, glowing bubbles of ionized gas. Some are bipolar, shaped like an hourglass or a butterfly, where the equatorial regions were denser and the polar outflows punched through more easily. Some have multiple shells recording several distinct episodes of mass loss. Some have filaments and knots and jets. Some have spirals. The Ring Nebula in Lyra, perhaps the most famous of all, looks through a small telescope like a tiny smoke ring in the sky. Through larger instruments and space telescopes, it reveals a complex nested structure, a barrel-shaped shell of glowing gas, with the white dwarf at its center like a hot blue eye. The Helix Nebula in Aquarius is sometimes called the Eye of God, a nickname that, while not astronomically rigorous, captures something of the feeling it evokes. A vast glowing iris, over 2 light-years across, surrounding the tiny remnant of the star that made it. The Cat's Eye Nebula in Draco has concentric shells of gas surrounding a complex inner structure of jets and arcs, recording thousands of years of episodic mass loss in luminous detail. Each one lasted only about 10,000 years before the central white dwarf cools enough that its ultraviolet output drops and the nebula fades. 10,000 years is nothing on astronomical timescales. These are fleeting things, brief and brilliant, like a last flourish before the quiet. And then the white dwarf remains, alone, roughly the size of the Earth, but carrying approximately the mass of the Sun, a density almost incomprehensible. A teaspoon of white dwarf material would weigh several tons. The white dwarf is made primarily of carbon and oxygen, the ashes of helium fusion. It has no fuel left to burn. It is supported entirely by electron degeneracy pressure, the same quantum mechanical effect that governed the helium flash all those billions of years before. But now there is no helium flash coming. There is no next chapter. The white dwarf simply exists, cooling slowly, radiating away the heat it accumulated over its long life. Over billions of years, it fades from white to yellow to orange to red, and eventually, in the very far future of the universe, it would cool entirely into a dark, cold object called a black dwarf, a cinder, invisible in the dark. Though the universe is not yet old enough for any black dwarfs to exist, the oldest white dwarfs are still warm, still faintly glowing, still carrying the heat of their former lives. There is something I find deeply restful about the white dwarf. After all the drama of the red giant phase, After the thermal pulses and the mass loss and the helium flash and the nucleosynthesis and the planetary nebula, what remains is something very simple, dense, quiet, slowly cooling. No more reactions, no more transformation, just the long, gentle release of stored heat into the cold of space. A star, finally at rest. Think about the full arc of that journey. A cloud of gas collapsing under its own gravity, igniting into a star, burning hydrogen for billions of years, swelling into a red giant, flashing and pulsing, building new elements and scattering them into space, glowing briefly as a planetary nebula, and then settling at last into a quiet white dwarf. From gas cloud to cinder, across billions of years, the star does nothing but obey the laws of physics. It has no choice in the matter. It simply does what its mass and composition and the laws of nature require it to do. And in doing so, it transforms the universe. It builds new elements. It seeds the interstellar medium. It lights up its surroundings one final time, and it leaves behind something that will persist quietly for longer than we can easily imagine. There is a parallel there, if you want to find one. Lives that transform their surroundings simply by following their nature. That leaves something behind, that in their ending make a kind of beauty, but perhaps that is enough thinking for tonight. You have traveled a long way since the beginning of this video, from the first quiet expansion of a hydrogen-exhausted core, through the helium flash and the horizontal branch, through famous stars with ancient names, through the chemistry of elements built one neutron at a time, through the strange discoveries of asteroseismology and the open questions that still sit unanswered in the literature, and now here, to the very end, to dust grains smaller than bacteria carrying messages from dead stars, to glowing rings of ionized gas, to white dwarfs cooling slowly in the dark. The night is deep now, the world outside is quiet, and somewhere overhead, through the ceiling and the atmosphere and the vast dark ocean of space, red giants are glowing their amber glow, building their elements, shedding their dust, pulsing with their slow, rhythmic breath. They have been doing this for billions of years. They will carry on long after tonight. And you, for now, can simply rest. Let your body be heavy. Let your breath come slow and easy. Let whatever thoughts are still moving through your mind become softer, less insistent, more like shapes than words. You don't need to hold on to anything right now. Not the facts, not the images, not the questions. Let all of it drift, like dust grains drifting outward through a stellar envelope, slowly and quietly, into the dark. And so we come gently to the end of our journey tonight. We have drifted together through some of the most extraordinary corners of the universe, through the physics of ancient stars, through the quiet drama of a helium flash hidden deep inside a stellar core, through the amber light of Arcturus and the long trailing tail of Mira, through the patient chemistry of neutron capture, through magnetic fields threading through stellar interiors, and finally out to the edges, where dust grains smaller than bacteria carry the memories of stars that burned out before our world existed. It has been a long and quiet journey, and I hope Somewhere along the way, your eyes grew heavy. I hope the words became softer, more like a gentle hum than a clear signal. I hope your body found its way into that comfortable, still place where sleep begins to arrive on its own terms. If you are still awake, that is perfectly all right. Sometimes the mind needs a little longer. Sometimes it wants to linger in the images for a while before it lets go. That is fine. There is no hurry. The music that follows will give you all the space you need. Let it carry you the rest of the way. Let your mind wander wherever it would like to go, into the amber light of a distant star, or simply into the soft, familiar dark behind your eyes. You have done nothing wrong tonight by being awake. You are simply a person lying in the dark on a small planet under a sky full of ancient light. And that is a rather wonderful thing to be. From all of us here at Orbit into Sleep, thank you so much for spending your night with us. If you enjoyed this journey, a like and a subscription means more than you know. It helps other restless minds find their way here on their own quiet nights. Sleep well, sleep deeply, and we will see you among the stars again soon. Good night.